Thanks, Megan, and welcome. In addition to the announcement of me, I would want to highlight that the presentation I do is created together with my colleague, Dr. Alexander Stock. He's our technologist, and a lot of the news I'm going to share is based on his valuable work. So just to be clear on this is not just Klaus Lang, this is also Dr. Stock. So let's jump into it. So first, what am I going to show? I would want to talk about an electric powertrain, so just give you a brief introduction what my definition of that is. And then we will jump right into how we do power calculation, and that is cycle-based. And in order to understand what that does and what it not does is we need to talk a little bit about cycle detection. How do we find and understand cycles? And based on this, I will then go over on how this know-how of cycles can be used to shorten test times. The first real-world example I'm going to explain and explore is how to speed up efficiency mapping with a method which is called cycle-based recording. And then further on, I will elaborate on a second method to speed up efficiency mapping by using dynamic electric power measurement. And both together then will allow you to really significantly shorten the test time you spend when you drive, when you test a drive, when you characterize a drive, when you do mappings. So, electric powertrain, just one slide how that typically is made up. You have typically a drivetrain which is made up of, let me take a laser pointer. I think that is the laser pointer, yeah. Which is a power source and an inverter and an electric machine. And in order to understand that drive, you at least need to measure a few parameters, typically voltage and currents out of the power source, voltage and current from the inverter into the drive, and obviously the mechanical parameters, torque and speed, out of the drive. And then there are a lot of secondary parameters you also might want to measure, like temperatures in the machine, in the battery and in the inverter, vibration signals to understand the NVH characteristics of your drive, and that is also then done with potentially a microphone. So that is what we are talking about today, how to measure faster at a typical electric drivetrain. So what is the foundation of that? The foundation is something what we call cycle-based calculation. And what does this do? Conventional power analyzers, which are on the market for decades already, use basically an analog PLL to track and trace the fundamental frequency, which in most of the cases, in most of the applications, is just 50 or 60 hertz coming from the grid. Yeah, and these grid frequency are changing only very slightly and very slowly. So these whole analog PLLs which are used are not capable to follow a fast change in the frequency. Yeah, so these conventional power analyzers do a real good job if you are in a steady state load condition, no doubt. Yeah, but when frequencies are changing, they have a problem. And also they work time boxed, meaning most power analyzers measure a time window of 100 milliseconds, and then within that 100 millisecond, they calculate the power and give you that result. Yeah, so they have a fixed time window in which borders they are measuring, and that is independent from your input signal. They always measure at a certain time boxed frequency. Now we have a completely different approach to that. We really have reinvented the way to do this, meaning we have a digital algorithm which detects the cycles in real time. So we do not do a time box and then try to find a frequency or so, but we in real time are detecting cycles. And you see that in this example, the green trace is a current in a drive with all the distortions on it, switching frequency, ripples, and whatever you see. And the red trace is actually the output of this algorithm we are using, which detects the cycle of this current in real time. Now, that's a nice statement that we do that, but what is the practical use of that, and how do we prove it's really working? Well, the practical use is easy explained in the right-hand picture, because here you see the startup of a machine. Yeah, and the startup of a machine is definitely something like a half wave or something like that. Yeah, and the red trace here indicates already here in the startup period that we have a cycle and we will do power calculation on that cycle. Traditional power analyzer will need at least a few cycles till it can drag with its analog PLL to that frequency, and it will probably give you a reading back here, the first reading, and you will be completely blind at the startup. So that's one important point that we can measure at startup. The next slide goes a bit into more details on this, explaining what happens if our algorithm would fail. Yeah, and we have introduced a very easy check to prove that we detect each and every cycle. So we calculate this red trace, which you did see in the picture before, which we call the cycle master trace. And then, as a little trick, we calculate the frequency of this cycle master trace. And when you think through that, you will figure out that this cycle check trace needs to have the same waveform as the speed in an electric drive, because it's basically the fundamental frequency on the electrical side, whereas the speed is the same, just with a few factors in it, like the pole pairs and a potential slip. But the wave shape needs to be the same. And that's what you see here. We have a drive up of a drive and a steady state, and a drive up, steady state, drive down. And this cycle check signal, the frequency of the cycle master, has the same wave shape as the speed signal. Now, what would happen if we fail to detect a cycle? And there are only two possibilities. You can either miss a cycle, so there is a cycle, but we don't recognize it, or you have only one cycle, but we detect more than one cycle. So these are the two possibilities: missing cycles or extra cycles. Now, as we calculate the frequency of the cycle master trace, a missing cycle will halven the value of this cycle check signal, and an extra cycle will double the value. And that means that such missing cycles will be immediately become visible in the cycle check trace. That's what you see here. There was a missing cycle here, missing cycle, extra cycles. And just to be clear, I needed to work hard to get these cycle detection to fail. I really need to do dirty tricks to make it fail. It's really robust. It does its job in 99.9%, but in these rare cases where it would miss a cycle or detect an extra cycle, you would see that immediately. I mean, there is no way you overlook this missing cycle here. Yeah. So the left picture shows everything is okay during a 1 minute run up. Every single cycle is detected. The right picture indicates there were a few cycles missed and there were a few extra cycles detected. And then again, if you look in the math, once you can prove that you have all the cycles detected properly, the rest of power calculation is just plain math. There is no more room for error in the rest. Yeah. So the only big error you can introduce into your power measurement is wrong cycles. And that's why power analyzers very often fail in run-up periods or in fast changes of the speed, because they fail to track the cycle. Okay, that's all basic stuff, cycle detection. Yeah, and that's how we do it. Now, why can we use that to speed up efficiency mapping? Let me explain the first example, which is, I think, the easier one. When you do a mapping, you drive your machine to different set points, and you can see that indirectly here in this current channel, because we increase the amplitude of the current, which means we increase the torque, and we also increase the speed of the current, which means we increase the speed. So this is multiple set points of the machine with different torque and speed values. And what you then do is you measure at the first averaging interval your power. And this averaging interval needs to be longer than your fundamental. Otherwise, you will get a wrong reading anyhow. So you set your power analyzer to that averaging interval, which covers your slowest speed. And then you use the same averaging interval over and over again to measure at different set points. That's how each and every power analyzer nowadays work. Yeah. So you drive a machine to a set point, you wait for the set point to stabilize, you average all the cycles within that interval, and you repeat that. And the problem is that this delta T is always the same and pretty long. And if you run the math and you say, let's make 1,000 set points, a map of 1,000 set points, and you want to have a change time of half a second between the set points, and then you wait for half a second till your reading has settled, and then you measure for 2 seconds, that gives a total test time of about 3,000 seconds. Yeah. Now, how can we improve that? Well, what we do is we do not measure at a fixed averaging interval. As we can in real time detect the cycles, we can also set our calculation based on these cycles. So we measure for one cycle at that speed, then the test rig is driven to the next set point, and again we measure only for one cycle, and we measure for one cycle, and we measure for one cycle, and we measure for one cycle. So the test time, the actual measuring time, gets shorter as the frequency or the RPM of the machine increases. And as we do a shorter measurement, you can then, in a second step, also keep your set points stable for a shorter point in time, period in time, sorry. First measuring interval, second, third, fourth, fifth, and so forth. And you see that not only the measuring time is decreasing, but also the gaps between the different set points are decreasing. And if you run the math again. Yeah. And you just make the assumption your first measuring point is basically the same as with a fixed averaging interval. And if you would go to infinite frequencies, your last measuring interval would be 0. Then you come up with a pretty simple formula, yeah, that even if you have the same change time and the same settling time, you already save about 1/3 of your test time. Just by going from fixed time interval measuring to fixed number of cycle measurement. Pretty easy change and already saves 1/3 of your test time. How does that look in a real setup? Well, you need to sync the power analyzer with the automation system because the power analyzer needs to tell the automation system that it is ready with the last acquisition so that the automation system can advance to the next set point. And that's what's shown here. So you have here 3 signals: current, torque, and speed. And you see when torque is increased, the amplitude of the current is increasing, and when speed is increased, the frequency of the current is increasing. And then your automation system drives to the first set point, and then it sends a signal to the power analyzer, which we call trigger arm. And then the power analyzer will wait for the next defined number of cycles, in this case 1.5 cycles, yeah, and measure. And when it's ready, it will send a signal back to the automation system saying trigger arm finished. And the automation system will advance to the next set point. In that period, the power analyzer might even execute an auto range to make sure that always the best range is used for the input signal. Next trigger arm, next acquisition, trigger arm finished. Next set point, next auto range. Then within the auto range, a trigger arm signal is sent. That will be delayed till the auto range is finished, and then delayed till the next 1.5 cycles become available. Test is done, trigger arm finished. And that is advancing through the whole test. So with just 2 signals, a trigger arm and a trigger arm finish, you can synchronize between the power analyzer and your automation system to get your test time down. Second example. In a conventional electric power calculation, you measure the line currents and the voltages at the input of the machine. You detect the fundamental cycle, so the rotational frequency, yeah, and then you do all your calculation based on an averaging over one or multiple fundamental cycles. That's what I've just shown in the example before, that you need to measure at least a half cycle and then do an averaging over a half cycle to get a proper power reading. Yeah. So that is so far the base of each and every power calculation. Go to the fundamental frequency and do an averaging over at least a half cycle or multiples of half cycles of the fundamental frequency. Now there is a way to speed that up, and that is a patented way to HBK, I have to say, and that is a method which is developed from my colleague Dr. Stock, and he did lay out the method that you can also do a power calculation based on the switching cycle. Yeah, so you measure the voltage and the current, you detect the switching cycle of the inputs, and then you do a result calculation based over one or multiple of the switching cycles. And that is, of course, way faster, because you typically have, let's say, a fundamental frequency of a few hertz or a few hundred hertz, but your switching cycle is typically 2, 8, 40, or 100 kilohertz, so way higher. Yeah, and with that, we can do the switching cycle, making the base of all calculations. So we calculate the RMS value and all the active, reactive, and apparent power, and even efficiencies based off the switching cycle. So because the switching cycle is way shorter than the fundamental cycle, we get way faster and more dynamic results. We call this actually dynamic electric power approximation. Why do we call this approximation? Well, the devil is in the details, as you know. Yeah, and this approximation, the accuracy you can achieve with that, is a function of the relation between fundamental frequency and switching frequency. Yeah, and there is a lot of math involved here, but I will show later in a real world example that it is pretty accurate, but it is not 100% accurate. And as said, it's a function of the relation between fundamental frequency and switching frequency. So let's see how that looks like. Actually, this is again an example of a startup behavior of a permanent magnet synchronous machine. Yeah, so it's a no load acceleration. There is no load at the machine, and you see that at the current, which in a steady state is really small. Yeah, still you have an initial current because the mass of the machine itself draws, of course, energy to become rotational. So the blue trace is the current, and the blue trace down here is the instantaneous power drawn from the machine to accelerate. And if you look on how power analyzers would measure that, the yellow trace is what you might see from a conventional power analyzer. Yeah, after 50 milliseconds or so, so the event is already over, the machine is already running, you see a value in a power analyzer. The red trace, however, shows that power measurement based on the switching frequency. Yeah. So again, the blue one is the instantaneous power. The red one is the power approximation we measure with our dynamic power based on switching frequency. The yellow one is the trace you will get out of a conventional power analyzer. So we have drastically increased the dynamics and the faster update rate for the power information. Second example, how that might look like. So we have a transition between different steady state operating points, and we will soon come to a constant change of steady state operating points like WLTP testing. So you have a jump in your power, yeah, and again the blue one is the now I need to make sure that there are up here is the instantaneous power. So this is instantaneous power, yeah. The blue one down here is the calculated power using the switching frequency, and the red one is the power calculated with the fundamental frequency. So a power analyzer with a time boxed system would still be slower. It might show up power over here. Yeah. So the yellow one is what we always do. That is cycle-based power calculation. So that's already pretty fast. But the blue one, which is the switching frequency power calculation, is even faster and really indicating the truth. Because there is a big peak in power here, which you don't see in that trace. Yeah. You see the same here, which is, I think, just a zoomed version of that. Yeah. So when you do a cycle-based power calculation, which so far with our system is the fastest you can get in the market, you still don't get the full amplitude of the power which is drawn by your drive to accelerate or to change torque in that case. Yeah. So we have a precise active power approximation during steady state and faster, more dynamic results. So you just are closer to the truth. Yeah. Now, how can that be used to accelerate testing? Because that's the topic of this whole PowerPoint here. How do we accelerate testing? Well, the trick is easy. The upper picture shows a typical torque and speed stepping to do a motor mapping. So you have a constant speed and then you change your torque and you do tests in every set point. Next speed point, all the torque points. Next speed point, all the torque points. So you go through all your different torque speed combinations in a fixed way. Now, as we have shown that we can measure dynamically, we don't need to wait for torque to settle. Yeah, we have speed points and we keep the speed constant, and then we just constantly increase torque. And during that increase, we measure while torque is changing. We still get accurate results due to our dynamic switching frequency-based power measurement. So therefore, within these very short speed steps, we can ramp through torque multiple times, and as you can see here, bringing down the test time to 20%. Now, how accurate is that? That question I already brought up, that we call this an efficiency or a power approximation. And this picture shows the same drive tested twice. Once with the conventional method, with steady state, set points, and then cycle-based measurement. And one with the dynamic method, with only speed being constant and torque just ramped through, and then all the measurements taken with the switching frequency-based method. Yeah, and yeah, this is probably not so easy to understand. Therefore, we made a differential map. So this is a map of the differences between the static measurement and the dynamic measurement. Yeah, and you will notice that the differences are pretty small in the interesting areas. Yeah, but you save about 80% of your test time. So this is, for example, very suitable for end-of-line tests, or for a series of tests you want to run pretty quickly before you finally might run the high accurate test, which takes more time. So you can really play with the two methods. Do I want to be very accurate at a very high investment of time, or do I want to be a little bit less accurate at 20% of the time only? That's a significant time saving. And even better, what you can do, and we did that as well, you can take data which you already have. So just imagine that you do not ramp up your system like here, but you take existing data which you might have from a WLTP drive testing. So you did drive randomly your drive already through all the set points during a real world drive test. So you already have data for all the set points. It was just not a set point test, it was a WLTP test. And now you use the method to do switching-based power measurement on the WLTP data, and you can get the efficiency map for free out of your WLTP data. So you basically don't do a test at all for your efficiency map. You use the data you already have for your WLTP testing, post-process it, and you get your map out of that. So you completely eliminate one mapping. We are coming to the end, summary and conclusion. So, and I think that's a single slide, just to repeat what I have said, and then we come to the questions and answers. I basically talked about three things here in this presentation. First, I explained digital cycle detection, how we do that, and what are the advantages of the customer, and also how it is traceable. Because we have this cycle check method, you always have proof that all the cycles were detected. And if you have all the cycles, your power results are okay. Second, based on this, the cycle detection, I explained what can be done with what we called cycle-based recording. So rather than doing efficiency maps based on constant time averages, we do constant number of cycle averages. And that already brings the test time down about 50%. Without any decreased accuracy, to be clear on this, cycle-based recording delivers the same quality of data in half about the time. Second, a more, let's say, method you need to be careful with is what we call dynamic power approximation. And there we do power calculation no longer based on the fundamental cycle, but we do it on the switching cycle. And therefore you get way more dynamic results, which allows you insights into transients and allows to do maps way shorter. Yeah, and especially I would say the insights in transients, it's extremely valuable because we can argue it's not as accurate in a steady state, but it gives you data which shows you the transient, whereas a conventional power analyzer does not give you any data. So you might have data which is only 98% accurate, but in the other case, you don't get any data. Yeah? It's different when we talk about maps. There, it's a decision you need to make. Do I want to save a lot of time and shorten my mapping time significantly? Yeah. Or do I still want to spend all the time as before to get the last % of accuracy out of it? And you have seen in my differential map that the differences in accuracy are always below 1%. Yeah, and you can do that on WLTP data. So that's the second method where you can significantly save test time down to a point where you can even eliminate tests completely and use existing data like from WLTP. Well, that's it